I would like to thank organizers for the invitation and to this very exciting meeting. Yeah, that's my title is about black hole hair, quantum and classical, which is directly related with quantum computing. But so I'm going to discuss two things. First, about skyrmion black holes. First would be about classical black hole hair, which by some mysterious reason was not paid much attention, although the solutions were known. This is with Alex Guzman. I don't know if he's here, supposed to be here, but yeah, there. And the second part of my talk will be about symmetries that we think we identified, a geometric description, geometric symmetries. These are so-called BMS type symmetries, asymptotic type symmetries that we think that we applied correctly to a black hole. And therefore we understand in classical geometric limit the origin of degrees of freedom that store black hole entropy in terms of Goldstone theorem. Okay? So these are two things. Let me start with the first one. Now the first thing is about global quantum numbers. There are so-called Folk theorems that state that global quantum numbers, in particular baryon number, I will be specifically interested in baryon number, okay, are incompatible with semi-classical black hole physics. Now, of course, there can be a different fundamental reason for non-conservation of baryon number. That's, of course, is perfectly fine. For example, grand unification, baryon number is violated, proton is unstable. Even in the standard model, there's no perturbative effects through the anomalies, baryon number is violated. This is perfectly fine. What we are going to identify, we're going to identify a loophole and show that actually there is no evidence that semi-classical black hole physics is incompatible with the conservation of baryon number. Okay? So, now let me review the standard argument. The standard argument actually is very elegant. I don't know who is the author of this argument because this is sort of this type of folk theorem. But the argument is very elegant and is based on the following Gedanken experiment, so the thought experiment. So you imagine you have an observer. This is observer Alice, and this does not work. I don't know, it doesn't work. So Alice can either create initially an arbitrarily big black hole, or simply take a black hole, already existing black hole, and throw baryons there in this black hole. So basically, initially, Alice can create a black hole with arbitrarily high amount of baryon number. Okay, so you throw it in. It works. Great. Thank you. So then Alice waits until the black hole evaporates. Now the point is that since the evaporation is thermal, and this is very important in the standard argument, that the evaporation is thermal, at least approximately thermal. Okay, small corrections are not so important. So it's approximately thermal up until the fixed scale, the Planck length, or whatever is the cutoff of your theory. Okay, let me assume that it's Planck length. So this means that no matter how big is the black hole, initial black hole, and no matter how high is the baryon number that you endowed to this black hole, the black hole has to wait until it becomes of a fixed size given by the ultraviolet scale of your theory before the substantial departure from thermality can take place. Now, when evaporation is thermal, you cannot return baryon number. Why? Because even if baryon is massless, sometimes people confuse this. They think that because baryon is massive. No, this has nothing to do with baryon mass. Because in the thermal evaporation, number of baryons and antibaryons produced, average, they are equal. Okay, the average number of baryons and antibaryons produced is equal. So you cannot create a net baryon number. So correspondingly, this clearly tells you that there is some problem, because obviously no matter how big was the initial baryon number, black hole has to wait until it becomes of the Planck mass to have a chance to return it back. And then there is no way to return it back, okay, because of many reasons. Now, some people entertain this possibility of remnants, but remnants do not withstand standard quantum field theoretic arguments. Okay, so therefore, I'm not considering remnants at the Planck scale. So therefore, the conclusion is that the baryon number cannot be a conserved symmetry in the presence of semi-classical black holes. So this is the standard argument. Now, the standard argument relies on two important assumptions. Okay, first is that evaporation is thermal, radiation is thermal, Hawking radiation, and moreover that it's thermal up until the fixed ultraviolet scale of the theory. Okay, so in other words, you see, this is very important. Then the moment when black hole has a chance to depart, to substantially depart from quantum thermality, is fixed by the theory. It's not the characteristics of your initial black hole. Why? Because it assumes that there is no such thing as baryonic hair of a black hole. Okay, so baryon number doesn't produce any hair. Correspondingly, this assumption looks justified because the metric is Schwarzschild. And in Schwarzschild metric, we know we can redo Hawking's computation, and we see that the operation is thermal. Okay, all the way till the Planck length. Now, I will denote by xh the size of the horizon, the radius of a black hole, horizon size. And so these are these two assumptions that I just said. Okay, no baryonic hair and no deviation from thermality until this point. At the same time, it is known that there are examples of black holes with skyrmion hair. Okay. These are, on their own, these are extremely interesting solutions. Now let me remind you what skyrmions are. Skyrmions are solitons that appear in sigma model, in SU2 sigma model, in which you have Goldstone bosons, pions. These are pions. And skyrmions are pionic solitons. Okay? So they are topological. This is this so-called Skyrm Lagrangian. U is an unitary matrix of SU2. Okay, it's a field which depends on pions, and so this is Skyrm Lagrangian. And this Lagrangian is known to give rise to solitons. Now, these solitons were introduced as a description for baryons in QCD. So baryons were considered as solitons of Skyrm Lagrangian. Now there is an important scale is the pion decay constant and the coupling, and so this sets the length scale, the typical characteristic size of the skyrmion, and the mass of the skyrmion. So the skyrmion is a configuration in which it's very simple to understand. So you have 3 pions, and these 3 pions, they form a hedgehog. Okay. So 3 pions form a hedgehog. They are directed radially. With the skyrmion function, f of r is a scalar function which interpolates from certain value at 0 to 0 at infinity. Okay. Now the thing is that skyrmion is topological. So for simplicity, I'm considering massless pions, massless quark case. But skyrmions continue to be topological even if pions are massive. The only difference is that after this characteristic scale L, the function, the profile function drops either exponentially or as a power law. In the massless case, it drops as power law. Now the skyrmions, they carry topological charge. In this theory, we have topological Chern-Simons current, and there is a corresponding topological charge. Now, topological charge, of course, is a space integral, so it must be 3 here, sorry, from the 0 component of the current. Very good. Now, based on Skyrm model, now, of course, it's natural to ask this question, what happens with skyrmions when we include gravity? And there was a discussion here about this hair that there was solutions found with skyrmionic hair in which you have event horizon inside the skyrmion. Okay? So you have outside the halo of these pions of skyrmion field, and there is a black hole inside. Now notice that the halo, the size of the halo is not fixed by Planck scale. Has nothing to do with the Planck scale. It's fixed by the QCD parameters. It's by the scale L, which is essentially a QCD scale. Now, correspondingly, there are these solutions with the skyrmion here. I will not present all these solutions, different regimes, different solutions. So there are these spherically symmetric ones. The functions, asymptotic values of the functions are, and this is a function, as I said, this is a profile function that goes to 0 at infinity. So in the massless case, it goes like 1 over r squared when r goes to infinity. Now, you can say, oh, wait a minute, but if there are skyrmions, and skyrmions are describing baryons, okay, then this should provide a loophole from the standard argument. Why? Because now there is a logical possibility that once, so your initial black hole doesn't have skyrmion hair. So the skyrmion is inside. There is no classical hair outside. But since there are explicit solutions in which black hole is smaller than the skyrmion, why there is no such a logical possibility? When I start from this black hole, eventually I end up with this type of configuration. In other words, black hole evaporates, it reaches the size of the skyrmion, then after that skyrmion hair grows inside out, and black hole continues to evaporate, but returns back the baryonic charge. And this happens at the scale L, which has nothing to do with the Planck scale. Now already this provides a loophole from the Folk theorem. Of course, this does not prove the opposite. Yeah. They are stable, right. So people, yeah, exactly. Sorry, I should have mentioned that. Right. These are stable configurations. Okay. I don't know how complete the analysis was of stability, but nobody discovered any instability in these modes. But then I will provide additional argument, and this will be the key of the talk, why they are exactly stable. Yeah.
Make the black hole big enough, it swallows the planets, the black hole evaporates, and then spits out the planets?
No, yeah, that's the point. Yeah. Because since you have, the planets are not, but you have to make two distinctions. Now, planets are not static hair, okay? This is sorry? Yeah, sure. So, right. So, if you had a static hair, stable, planets are not stable here because you can perturb them, and so you can end up on a trajectory in which they will become swallowed. Now, of course, if you had a solution of a black hole in which black hole has a dust cloud outside, and this dust cloud is stable under deformations, yes, I would tell you that you should take this into account. Doesn't prove that this will happen. This is a separate story. But, of course, if you have a stable dust cloud which is not falling into a black hole under perturbations, of course, you should reconsider the argument. I think that's obvious. You should see what happens, right? I mean, based on what you are ignoring this type of configuration then, right? If you start with. Now, the standard thing, the standard Folk's argument ignores this because there is an assumption that there is no black hole configuration with baryonic hair. That's why they ignore it. But once somebody tells you that there is such a stable configuration, you cannot ignore. Now, I want to provide much stronger argument. Okay, so so this is already a warning sign. Here I'm giving a warning sign. This is not a proof, but this is a potential loophole because you see, this tells you that we have to be careful. All right. See, actually, this is what I just said. So this is a logical possibility that the black hole goes down and then skyrmion hair appears. Now the question is, and this addresses your question, is this just a logical possibility or is it a must? Okay? And let me create a situation in which this is a must. This is the point. Okay? Now, skyrmion, so there is, as I said, there is such a thing as skyrmions were originally introduced in order to explain baryons, but we want to do better than that. Therefore, we adopt picture of large N QCD. Why? Because in large N QCD, skyrmions are under much better control. And actually, it is believed that correspondence is excellent for large N. Okay? So for large N, what do you have? And this is mainly by Witten and others. Now, what happens? If you have QCD with a large number of colors, of course, there is U1 baryon symmetry. This symmetry is anomaly free in QCD. And there is a baryonic current. Now, the mean field description of this baryonic current is the skyrmion current. Okay, so there is a mapping between. So in other words, think in the following way. Think that you have two observers in QCD. So we are in QCD. Okay, so you have two observers, Alice and Bob. And Alice is an observer which is ultraviolet observer. Okay, Alice thinks in terms of quarks and gluons. Bob is an infrared observer, thinks in terms of pions. Okay, now Alice has a baryonic current in her theory. Now, what does this baryonic current in her theory correspond to in Bob's theory? In Bob's theory, there are no quarks. In Bob's theory, the corresponding current is the skyrmion topological current. So there is a mapping from Noether current of baryons to a topological current of skyrmions. Okay? Now, this was again known, of course, but nobody really made a connection to use this for trying to find a loophole in the Folk's theorem argument. Another step which I could not find anywhere discussed in the literature, also Alex could not find it, is the following. Now, typically the skyrmion charge is introduced as a volume integral. Okay? I mean, volume integral as usual. No? You have volume integral out of the zero component of the current. But you can make this observation that the zero component of the current is actually a Hodge dual of a two-form. So the current is conserved trivially precisely because it's an exterior derivative of a two-form. That's why this current is topological and is conserved. Now, if you look closely, you can identify a unique two-form which is well-defined everywhere. There is a unique two-form well-defined everywhere because two-form you could divide up to a constant, and there is a constant, one constant in which this two-form is well-defined everywhere, and this is this two-form, S mu nu. Of course, you can define it up to an exterior derivative again, which is not contributing into the charge. Now, the point is that once you have this two-form, of course, you can rewrite baryon or skyrmion topological charge or baryon charge as a surface integral over a two-sphere. Now, this is a bit surprising and interesting. Of course, there is nothing surprising that you can rewrite this as a surface integral. But this opens up a completely new possibility. Because once you rewrite something as a surface integral, then this falls within the standard, not completely standard as I will demonstrate, thing that you can measure this thing at infinity. You no longer need to go and see what is happening inside the skyrmion. So once you prepare a skyrmion, this charge is non-zero, and then it's forever. Because an observer at infinity can monitor it. And here is the point, okay? This is, however, monitoring this charge is not at all a trivial business, okay? Let me explain this. No, it has nothing to do with the horizon. I'm discussing a simple skyrmion. Forget about black hole. This is a skyrmion discussion, okay? Skyrmion charge is a surface integral. This is, by horizon you're confusing yourself because just normal QCD in QCD. Consider in QCD skyrmion, okay? In QCD there is a perfectly smooth configuration. There is a perfectly smooth two-form, okay? And you can define a topological charge of a skyrmion as a surface integral, period, okay? Now this is a charge which you can evaluate over a two-sphere. Now, how do we evaluate it? Now, you see, what is interesting? What is interesting is that at infinity, the f of r goes to 0. Okay? So this function could fall arbitrarily fast when r goes to infinity. You don't care, because this object captures the winding number. the topology. You see, this is the point. The point is that it's very similar to Aronow-Bohm effect, as we will see immediately, okay? Because remember what happens in Aronow-Bohm case, right? In Aronow-Bohm case, you have a magnetic flux, and you have nothing outside. There is nothing classical outside. There is nothing that you can locally measure. Even quantum mechanically, there is nothing that you can measure locally. The only way to capture topology in Aronow-Bohm effect is to do an interference experiment, a global measurement. So it's a quantum measurement which reveals that you have a classical magnetic flux inside, okay? Right? So it's exactly the same here. How do I do this measurement? Well, it's completely straightforward generalization of Aronow-Bohm effect. Now, in order to capture Aronow-Bohm effect, what you do? You have a flux, and you take a particle, probe particle, right, which has a charge which is fractional of the magnetic flux. And you take this particle around, and you get a phase shift, okay? Now, here we are dealing with a two-form surface winding, not simply a phase. So what you have to do, you have a skyrmion, you have to lasso the skyrmion by a string, okay? So instead of taking, you see, in Aronow-Bohm, it's like dual to Aronow-Bohm. In Aronow-Bohm, you have a particle, and you are taking particle around the solenoid. And here you have to take solenoid loop and take it over a particle, okay? So the solenoid loop is a string. So you need a string, a spectator string, to which these two form couples. So this is the word volume of the string. The two form couples to this word volume. And now we can perform our Aronow-Bohm time experiment. Yeah. 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 Mm-hmm. Yeah, at infinity. Of course, that's the whole point. Pi is what tells you about topology. Is this one? No, what do you mean? Why? I mean, this is up to a normalization. I don't understand what you mean. This is, I chose, here should be pi times b. B is the number. Now, I choose simply winding number 1. Is that what you're asking? Yeah, it's just integer times pi, and yeah, I just choose this integer to be 1. Sorry, I should. Of course. Right, that's right. Yeah, for simplicity, I'm just looking at the winding number 1. Now, this is the interference experiment. Of course, so in other words, you have to do Aronow-Bohm experiment, but instead of using particles, using strings, okay? All right. Of course, it's not so easy. I mean, you need to manufacture strings, but that's just a technicality. So in other words, any process in which the string, topologically non-trivially, this is a string loop, captures the word volume of the string, captures the skyrmion, you get an Aronow-Bohm phase shift, 2 pi g times b, and you can detect that you have a skyrmion. This is another version of this experiment. Now, this is not a string. This is not a Feynman loop of a string. This is just the illustration of the interference experiment. So you have string source that is shining strings, and then sometimes strings go without enveloping the skyrmion, and sometimes they go enveloping skyrmion, and then they create an interference pattern on this screen. Okay. Okay, and then you get the phase shift. You can also have vacuum processes. Like, for example, you can have a vacuum process in which your string materializes from the vacuum and closes the skyrmion and disappears. Then you get the phase shift. But now you see, you are in a full control. Because what happens? Now let me do the following Gedanken experiment. Let me start with the skyrmion, which is not a black hole. Okay. And sprinkle some matter around it. Then Alice can measure the skyrmion charge at infinity, and then whatever happens, this is forever. Then you can do whatever you want with your skyrmion. You can collapse it into a black hole together with surrounding matter, or throw it into a black hole, whatever. The surface integral remains, and you are under the control. Okay. Now, of course, in this case, the reappearance of the skyrmion here is a must, because now you have a winding number which has to be conserved topologically. And So you wait, the black hole evaporates, and then at some point this Kirmian hair must be revealed. Of course, it's natural to assume that it gets revealed when you know the existing solutions with Kirmian hair. Not before and not much later. Now, so what is the conclusion? The conclusion is that, okay, let me summarize what I have demonstrated so far. So we took a limit of a theory which we can control, which is well understood. We took large NQCD, in which we can control the baryon-Skyrmion correspondence extremely well. And in that theory, we have demonstrated that there is an Aronoff bomb phase which can control the existence of the baryon number inside or outside of a black hole. Okay? Now, of course, we can ask from here many questions. This opens up many questions. I mean, how important is it that in standard QCD we only have n equals 3? I don't think this is terribly important, because qualitatively this will not change the story. Of course, we can have corrections, but qualitatively will not change the story. But however, this is something to be studied. But obviously, you see, if this is true that baryon number is conserved by black hole physics, that there is a topological charge that you can associate to baryon number, which you can measure at infinity by Aronoff bomb effect, of course, this changes many things in astrophysics. Because obviously, I mean, if baryon number continues to be a valid baryon number inside the black hole, then the future of black holes is a little bit modified. And there are many interesting questions that are opened up by this observation. Okay. But again, I mean, there is a very general message that we have to be extremely careful when we make statements about seemingly global symmetries which may have underlying topological protection. Okay. Of course, this is not a global symmetry. I'm not claiming that because of this every global symmetry is respected by gravity. But baryon number is a special global symmetry which has underlying hidden topological protection. And this is very important. Now, let me continue to another part of the story. How much time do I have, by the way? Half an hour. Very perfect. You see, I split it in just right. Now, the second part of the story is again related with the hair, but in this particular case, I will not assume any additional hair, any additional quantum number in the theory. Pure gravity. I will discuss pure gravity. Now, it is becoming evident, and we think we made some progress and we understood certain things. Of course, there is a very long way to go, but we understood certain things about geometric description, even the classical description of the degrees of freedom that store black hole, that carry black hole hair and correspondingly black hole entropy. So this is a black hole hair from super horizon super translations. Recently there was some activity also by other groups. I will cite them by Hawking, Perry, and Strominger. But there are differences in our statements. Okay, the general direction is the same. Okay, we both understand that there must be some geometric way to describe degrees of freedom that store black hole entropy. But there are differences which I want to highlight. Now, as you can see, transition is very sharp because these transparencies are not written by me. I borrowed it from collaborator Dieter Lust. Correspondingly, since these are his transparencies, sometimes my name appears and his name is abbreviated. So this is, I'm sorry, I cannot change this because, and you see these are very nicely written. Now, what is the point? So the point is the following, that, okay, we think that we have identified a transformation, purely classical limit, which is spontaneously broken by black hole vacuum. Okay, so these are transformations that are spontaneously broken by black hole vacuum, and corresponding Goldstone degrees of freedom are the degrees of freedom that store black hole entropy and hair. Okay. Now these transformations, we call them A transformations with capital A. And in classical limit, they reveal that there are infinite number of classical charges correspondingly which are responsible for infinite black hole entropy in the classical limit. So what happens is that there are these translation generators, which we call A translations, okay? And these A translations, they act on a black hole state, black hole vacuum, okay, the ground state of a black hole, and they shift it. Exactly in the same way as this happens in Goldstone model, okay? You have a Goldstone model with U1 symmetry broken, what happens? You have the continuum of the vacuum states, you act with the generator, and you take it, which takes you from one vacuum to the other, okay? Exactly the same thing. So then you have infinite number of independent Goldstone degrees of freedom, and they are the ones that store information in a black hole. Now, classically, you have infinitely many generators, and their expectation values by consistency vanish classically. What happens quantum mechanically is that quantum mechanically they are lifted. And their expectation values are non-zero, and their number correspondingly becomes finite. The number that fits within the gap that accounts for the black hole entropy. Now, in this we differ from everyone because we appreciate that these transformations are lifted by quantum corrections. They are not, because other people, from what I understand, they are looking for symmetries. We're not looking for symmetries. We're looking for symmetries which are, we are looking for transformations which classically give you degeneracy, but quantum mechanically they are not symmetries. They are not, sorry? Of metric, right. Now, okay, so let me, so here are some notations. Okay, so these are some of the papers. So notations, okay, this will be gravitational radius. This is Planck length. And this is black hole entropy. Now, black hole entropy goes as R square in the Planck length units. Of course, I'm not including here 4. We had discussion this morning. Now, immediately from here, you notice, and there was a conversation here, right? Here's an explicitly, you see. What happens is that the black hole entropy in classical limit is infinite. Because if you want to keep the mass of a black hole finite, Newton's constant finite, correspondingly Schwarzschild radius finite, Planck length goes to 0, and correspondingly, in semi-classical or classical limit, black hole entropy becomes infinite. Okay? Now, this unambiguously is telling you is that whatever things, you shake your head because of this statement, or sorry? Not to 0, to infinity. It goes to infinity because let's define, right? What do we call semi-classical or classical limit? Okay. Now, what is classical limit? If you want to keep mass finite and Schwarzschild radius finite, I think it's totally obvious that this goes to infinity. Okay? Huh? Maybe. Now, let's define semi-classical limit. Now, different people sometimes like different definitions, but semi-classical limit, sensible definition of semi-classical limit is the following: that you fix geometry and you consider quantum particles in the fixed geometry. Okay? Now, this you can only, if you want to do it consistently, the only possibility to do this consistently is you take black hole mass to infinity, you take Newton's constant to 0, and you fix gravitational radius. Okay? This is, and you keep h bar finite. Right. In this limit, obviously the entropy goes to infinity. Okay? Then tell me what you call semi-classical limit. Yeah, that's what it is, maintaining. No, the semi-classical limit means that you ignore back reaction from quantum flux. No, then okay, then we're talking about different things.
Because we compute the energy momentum tensor and stuff it into the field equation. This has been done by, I guess, hundreds.
Yeah, that's why you get an incorrect result. That is the precisely point. This is precisely point. You see, the point is that we are not working rigorously. If you move on to do rigorous computation, we have to be extremely rigorous. Now, let me define the semi-classical limit as I like it, and I will be fully consistent with my definition. My definition is that if I want to ignore back reaction from quantum particles on the background geometry, like Mesh-Bauer effect or whatever, I mean, it's this table, I want to ignore back reaction from here to here, effectively I'm working in the limit when this table is infinitely rigid. So I have to make geometry infinitely rigid. To make geometry infinitely rigid, this is what I have to do, because I have to take mass this is what I'm defining. And in this limit, it goes to infinity. Now, I'm perfectly fine if somebody wants to define in some other way, then it may be finite in that limit. Of course, the number of microstates becomes infinite and they become gapless. This is precisely the point. Look, I mean, the names do not matter. What matters is the content, right? Now, as long as we agree on the content, what I'm saying is that this is, in this definition, call this limit whatever you want. Call this classical limit prime or semi-classical prime. This is the well-defined limit. In this limit, as well as in classical limit, black hole entropy goes to infinity and the degrees of freedom become gapless. I don't mind if somebody wants some other definition. I'm perfectly fine. There's no problem. I mean, this is just, I want to be consistent with myself, not with others. You see, this is the point. And now, now notice the following thing. Let me, I don't have time to enter in this beautiful story of BMS because BMS sort of was a little bit, not really forgotten, but in the background, and recently was sort of reconsidered in this. Now, what is BMS story, right? So BMS is about asymptotic symmetries of S matrix, in particular Minkowski space, right? Now, BMS is telling us that Minkowski space is hugely degenerate, okay? In fact, infinitely degenerate. Now, of course, we can do this geometrically. Rigorously, we can define super translations rigorously, geometrically, and see these generators of the translation, stuff like that. But there is a very, very clear physical reason why you expect that Minkowski space should be infinitely degenerate. Why? Because, first, I can think of a Minkowski space as a limit of an infinitely massive black hole when the Schwarzschild radius goes to infinity. Okay? I can think of a Minkowski space as a near horizon, okay, geometry of an infinitely heavy black hole, if I fix G Newton. And since infinitely heavy black hole carries infinite entropy and it's infinitely degenerate, then correspondingly you understand that Minkowski space must have at least that degeneracy. But actually Minkowski space is even more degenerate than infinitely heavy black hole. Why? Because you can identify degeneracy of the Minkowski space without necessarily talking about black holes. Now, I don't know, you probably, I mean, many of us teach students and stuff that if I have a massless theory, for example, electrodynamics or spin 2 or spin 0, that doesn't matter. In a massless theory, vacuum is a coherent state, okay? So in a massless theory, you can define vacuum as a coherent state of infinite occupation number of zero energy quanta, of infinite wavelength quanta. And of course, that definition, you immediately see that it's degenerate. Why? Because you can change occupation number by, again, infinite amount, okay? And you go from one coherent state to the other, and those are orthogonal, okay? So correspondingly, the fact that Minkowski is degenerate, you see in several different languages. And so what happens is that you have transformations, which are these BMS transformations, okay? Let me stay in pure gravity at the moment, in pure spin 2 theory. And these BMS transformations acting on Minkowski, they give you Minkowski prime, or Minkowski tilde. So you have infinite number of orthogonal Minkowski states. Very good. Now the point is that we can go backwards. We can ask, by the way, this is a very general question, as I was commenting in the previous talk, because you see, the moment we realize that black hole entropy goes to infinity in classical limit, okay, we understand that whatever degrees of freedom carry this black hole entropy, in the classical limit, they become gapless. Now, it's a natural question to ask, in the classical limit, these gapless quantum degrees of freedom, do they admit geometric interpretation or they don't? A priori, you don't know the answer, because it could be that they don't admit geometric interpretation in the classical limit, may or may not, right? So this is the question that we're asking ourselves. And by the way, this question is completely independent, whatever is your favorite theory of black hole entropy or microscopic theory, okay? It's a general question, because all the microscopic theories, they converge into one classical theory, because GR is one classical GR, okay? So if there is a geometric interpretation of that degeneracy, you should be able to capture it at the level of GR, okay? This is the point, this is the question. Of course, it's not easy to capture it. Why? Because, as I said, simultaneously in the same limit, the charges should vanish, expectation value of the charges. So you get infinitely many charges with zero expectation values. And it's not easy to read them out in the geometric picture. So you should know what are you looking for. Otherwise, you may confuse yourself extremely easily, okay? Now, I think we managed to confuse ourselves, so let me convey our confusion. No, at the end of the day, I think we understood at least one possible description of this. Okay, so there are things that are matter of taste, okay, and the choice of coordinates. Let me just simply present the result, because I don't have much time to go all through these variations of the thing. The simplest that we could identify were in these infalling coordinates, okay? Then, in these coordinates, you can identify, now how you proceed. You want to identify translations that look like diffeomorphisms, but they are not, because of course diffeomorphisms are irrelevant because they are redundancies. So you are looking for something which is not a redundancy of the description, okay? In other words, you are looking for large gauge transformations. This is the point. So what happens is, in gravity, is the following thing, that in the presence of a null boundary, either horizon or the or Scri minus, any Minkowski boundary or the black hole boundary, diffeomorphisms, part of the diffeomorphism reveals large gauge transformations. Okay, they become large gauge transformations, and large gauge transformations are no longer redundancy; they are physical. Okay, now they are physical. They may or may not be exact symmetries of the theory. Okay, they may be approximate symmetries or exact symmetries. A priori, we don't know. This is what we are looking for. Now, okay, here is what we identified as a good candidate, at least for the part of degrees of freedom that accounts for the black hole hair and corresponding black hole entropy. We don't have a proof that this is the whole thing, because there may be part of transformations that we are missing out. That could be, okay? So it could be that something else is there and we just simply overlooked it. But this scales, has a right scaling. It scales like area. The number of these guys scales like area. So what is this transformation? This is the following transformation. Let me explain in the following way. You see, let's take this chair, or whatever, not chair, but whatever it is, okay? Okay, so now you see, I can take this object and place it on a Minkowski space, okay? Now, I can act on this, and this will give me a state, right? So this will be a state of whatever. I don't know what is this? I mean, what is this called? Some razor, okay. On Minkowski space, okay? So this is the state. Now, what I can do, I can act by a standard BMS transformation, the ones that I discussed before, okay? I act with standard BMS, and this will take me to a different state, okay? Of course, this state, because Minkowski is highly degenerate, I will have infinite copies of this state when I act by a BMS transformation, okay? But of course, this fact that I have infinite copies of this transformation, this tells me nothing about the entropy of this object. This object doesn't carry much entropy, very little, okay? In other words, this is a degeneracy which is there because of Minkowski degeneracy and has nothing to do with the intrinsic microscopic degeneracy of this object, okay? Therefore, we have to mod this out, okay, this degeneracy, otherwise we will get double counting, okay? So this is very important. So therefore, what we have to do, we have difference, we have to evaluate the difference or mod out the transformations that are relevant for the black hole horizon, okay, for the null surface which is black hole horizon, and we have to mod out the standard BMS transformations, okay, in order to avoid double counting. The resulting transformations, we call, they are given by this vector, and we call them A transformations. I don't know, the name is whatever it is, right? So what happens is that, so now what you have the following thing, that you have a black hole metric, and you have a transformation which you know that it's not a redundancy, okay, and it's not standard BMS, which keeps ADM mass invariant, okay? Now, these transformations are Goldstone bosons of the broken generators of by what transformations we are acting on a black hole. So, in other words, what we're learning is the following, that exactly in the same way as this object here breaks translation invariance spontaneously, and therefore if I act by a translation generator, okay, I shift it, okay, and I excite a mode. In the same way, black hole vacuum breaks spontaneously certain set of BMS-like translations, okay, super translations, super horizon, super translations. And this spontaneous breaking of these generators gives you infinite number of Goldstone bosons, okay? Now, these Goldstone bosons, which since we are in the classical theory, just like in the classical Goldstone model, this Goldstone boson is exactly cupless, okay? And there are infinite number of them parameterized by theta and phi. I thought I had this transparency before. I don't know. Okay. Anyway, so there is a beautiful one-to-one correspondence with the Goldstone model. It's really fantastic how nature works. So just exactly like in Goldstone model, what do you have? You have vacuum. You have a certain transformation which is spontaneously broken, which is not annihilating your vacuum, and it's taking your vacuum to the other vacuum. Exactly in the same way, there are these 8 transformations which act on black hole vacuum and take you from vacuum to the other vacuum. Correspondingly, there are infinite number of charges, but they all vanish classically, as they should. Now the question is, what happens quantum mechanically? Okay? Sorry. Anyway, so now the question is, what happens quantum mechanically? And here comes the extremely important point, which we want to really stress, and I think that is not appreciated in the rest of the literature, okay? The point is that if these transformations remain exact symmetries of your action, then they cannot be the right degrees of freedom for describing black hole entropy. Why? Because then black hole entropy would continue to be infinite even quantum mechanically, okay? This is very different from Minkowski space. You see, Minkowski space continues to be infinitely degenerate even quantum mechanically. Why? Because Minkowski space deals with infinite wavelengths, okay? The wavelength of the modes that are responsible for the degeneracy of the Minkowski space is infinite, and correspondingly, even quantum mechanically, they are not lifted, because infinite wavelength particle, even quantum mechanically, costs 0 energy, okay? But for a black hole, the wavelength is Schwarzschild, given by Schwarzschild. And quantum mechanically, necessarily, you will lift it, okay? So correspondingly, this cannot be an exact symmetry of the full Lagrangian, full action, because quantum mechanically must be lifted. Now, this very nicely resonates with the previous picture that Cesar Gomez, myself, and our collaborators were trying to develop, in which we're trying to develop black hole as a multi-particle state, as a state of many soft gravitons, okay? And but at the state of many soft gravitons at a very special quantum critical point, because this quantum critical point, as we have understood in many body physics, corresponds precisely to an enhanced entropy point, because you have enormous degeneracy of so-called Bogoliubov modes, and so there are dissimilarities. Now, whatever I said before is completely independent of this portrait, of this black hole portrait as a soft graviton state. If you don't believe that black hole has anything to do with n soft gravitons, that's perfectly fine. This is not changing anything I said before. But what I want to point out is that very nicely resonates with this picture, what we see. Because indeed, you see from many body side, you have a multi-graviton state at the quantum critical point. You have, of order n, almost gapless Bogoliubov modes, okay? And then from the classical side, you again see that you have the Goldstone modes, again gapless, which quantum mechanically should match this type of counting, okay? Now, okay, so here, coming back to the previous discussion about the, I have 3 minutes? Okay, all right, I'll be done in 3 minutes. Okay, so once you have a transformation, you can try now to evaluate charge of this corresponding to this transformation. And indeed, you find very nicely that once you, okay, so you evaluate, okay, of course you do something completely straightforward. You say, okay, I have a transformation which leaves, infinitesimal transformation which leaves bilinear of this graviton bilinear action invariant, okay? Let me quantize this transformation, okay, directly, and see how many do I get and what are the corresponding charges, all right? And, okay, you can identify corresponding charges. This identification of corresponding charges, again, very similar the way you can identify a charge in a Goldstone model. Because remember, what happens in the Goldstone model? Let me remind, right? In Goldstone model, I have a bottom of the Mexican head potential, right? And what happens is that I have expectation value of a phase. And when I do U1 transformation, okay, the expectation value of the phase shifts by a constant, okay? So I shift, I go from here to here in different vacua. Now, you can derive corresponding charge exactly same in the same language, and you can see that different vacua, from the point of view of each other, they correspond to coherent states, okay? So in other words, if I choose in a Goldstone model this vacuum to be my true vacuum as a reference point, then any other vacuum I can understand as a coherent state of infinite wavelength quanta with infinite occupation number. In a standard Goldstone model, I'm talking about U1 Goldstone. So exactly the same thing is happening here. It's really beautiful how physics is common for whether you are dealing with a black hole or a Goldstone model. It's really amazing. And you can see here is the exact expression. You see exactly that this is indeed a coherent state. Okay. Now, okay, so now comes a little bit of a speculation, okay, because we have to, now speculation part is that, okay, once you identify the charge, which is pretty rigorous, now after that, the expectation value of this charge you can compute in this state, and then you have to ask yourself, what are the charges that I should keep as legitimate representatives of the black hole entropy quantum mechanically, okay? And I must admit, we don't have a good criteria for that. We imposed on ourselves the following criteria. We said that all the charges with expectation values which are larger than 1 over n, we should throw away. Now, this, I don't know if this is fully legitimate or not. Anyway, this we made this assumption, okay? So I don't know if when we are throwing this away, we're also throwing away something important. Could be, okay? But this is the point. Okay, now, of course, if you do impose on you this type of restriction, then you can see that whatever these generators are, the charges, the number of species of these degrees of freedom scales like n, which is like area. Of course, we cannot compute the coefficient or anything like that in this analysis. We just see that this contribution coming from these guys scales like correctly. It could be that we are missing contribution of the similar order, okay, from some other sector which we could not identify. Again, I have to be very careful about this, okay? And, okay, so this is what I said. Yeah, number of states scales approximately to 2n and correspondingly, okay.
Feeding this cutoff? So that
Yeah, cutoff I'm feeding because otherwise I would go even more.
feeding so that you get something that you would argue is the right answer.
No, I mean, no, this is, we are not completely unreasonable, because you see, what do we see is the following. We have certain Qs, and these Qs, they initially all the states are degenerate, and then your gap is created, okay? Now you ask the following question. This is a fact. So if I continue forever, this gap grows. Now the question is, how many Qs should I count into the entropy? This is a question. I'm just asking you, if you tell me that I should count more, I will count more. I'm just saying that if I count these guys, then corresponding 2 to the n states will be crowded within the energy gap, delta E, of order black hole mass divided by the entropy. Okay? So it will be 1 over n of the black hole mass. That's what I'm saying. I'm not insisting that this is the correct answer. If you guys want us to include this, we will include that. If you give me a good argument that we should include more, that's perfectly fine with me. You are absolutely right. We are assuming, because of course we cannot include all of them, because sooner or later the gap will be so large that those states should not be counted as the microstates. I mean, microstates must be something that are crowded within certain gap, small gap. Now the question is, what is that gap? Honestly, I don't know the answer. Is this gap 1 over n, or is 1 over square root of n? What should I count? N is entropy, black hole entropy, okay? Right. So n is something that comes out to be black hole entropy, right?
Comes out, or you
No.
did you introduce it in the first place?
No, n is the, right, n is the parameter which enters. Why? Because these degrees of freedom, they have gravitational coupling constant. We are not introducing anything by hand. This is the point. Gravitational coupling constant of these degrees of freedom goes as usual, as you know very well. This is L Planck divided by the wavelength of these guys, R G squared. Okay? This is the gravitational coupling of these guys. Notice that this gravitational coupling is exactly 1 over the entropy, without any putting by hand. Okay? This is how 1 over n appears in this counting, right? Okay, n appears intrinsically as a coupling constant of these degrees of freedom. Okay, and the coupling constant of these degrees of freedom is an entropy. This is not an input. This is essentially a prediction of this framework. Now the question is, given this coupling, we can compute by quantum corrections. We can estimate what will be the central charge that these guys will develop. Okay, and okay, the point is that there is a gap, energy gap, and the question is by what I should restrict the counting of states. In other words, which states I should include as a legitimate entropy carriers and which I should not. And my understanding is that this number of states is for sure should be included. Why? Because they scale as 1 over n out of black hole mass. Okay. So in other words, you see, to put it differently, these are 2 to the n states which are crowded within the entire energy of one Hawking quanta. Okay? This is the point. So all these n states are crowded, like here, with delta E, which is essentially h bar divided by black hole size. Okay? A single Hawking quanta. So of course they should be counted. Because look, otherwise it's you see, otherwise after one emission time, you already emitting this. So of course they should be counted. But whether you should count more, I don't know. This is an open question. I mean, I would accept any suggestions, interesting suggestions. Now to conclude, unfortunately I don't have time to elaborate on more. But okay, so what we are discovering. Indeed, this picture gives us what you would expect. What happens? Classically, black hole has infinite number of hair, okay? Not 0, but infinite. But also people that were saying that black hole carries no hair were correct. Why? Because despite the fact that the hair is infinite, it takes infinite time to resolve it, okay? So therefore, you can say that there is no hair or infinite hair, okay? Now, so the resolution time is enormous. It also scales like n. Okay. Well, depends whether you want to count as start of resolution or finish of resolution. So it's either n or n square. But this is how the black hole accommodates its entropy consistently with the classical limit. Okay. Now this clearly shows us that, of course, very likely we are not capturing the entire story, and we're missing a lot of things, but it really gives us a strong evidence that we are on the right track because, because everything sort of matches very nicely. Okay, let me finish here.